I have an integral that I want to evaluate. It has a quadratic piece in the bottom, and in the top it just has a constant. So I'm not going to try to use a u substitution because I know the derivative of the bottom will have 1 power of x in it at least, and that's not showing up here. So what I'm going to do is complete the square on the bottom. So to do that, I'll take this -6, divide it by 2, and then square that. So -6 divided by 2 is -3. -3 squared is 9. So I want to replace x squared minus 6x with that plus 9. That will become my perfect square. And then since I added 9, I'm going to also subtract 9 to balance it out. And then keep this minus 16. So the purpose of the minus 9 is that I did not actually change the value going down here. I just reorganized it. Now this is x minus 3 squared. This is minus 25. And if this said plus 25 or plus some constant, then I know that I can get to arctangent if I first factor out that constant from the denominator, and then I let u equal whatever is being squared here. And I can rewrite this as a constant times 1 over u squared plus 1 and use arctangent of u. But I have a minus here instead of a plus, so it's a little different. It's not as immediately obvious. But if you happen to have a table of integrals that you can look at, then this would be one of the families of integrals that you might see on there. It doesn't take too long to figure out why this is true, but you have to learn about hyperbolic trig functions and calculate their derivatives and look at their antiderivatives and do a little bit of special algebra. This is not that complex, but you don't have to learn that stuff either. You can just read this off from a table. So for us, I can see that so the way this is set up, I need a constant squared minus a variable squared in the denominator. So I'm going to factor out a negative so that the constant moves over here to the left. And then I'm going to let u equal x minus 3. So let's rewrite this, first of all, factoring out the negative. So now it's in the form a squared minus u squared. Now we'll let u equal x minus 3. So du dx is 1. That means du is equal to 1 times dx. So I can just replace this dx with du. And I'll write this as 5 squared. 5 squared minus u squared. And then this just straight up becomes du. All right. Now I am in this form, so I can go right to that formula. I'll have a negative out in front. That's no problem. And then I just plug in 5 for a, and I plug in u. Instead of plugging in literally the letter u, I'm going to plug in x minus 3 because I want my final answer in terms of x. So I got 1 over 2 times 5. Natural log, absolute value of 5 plus u. 5 plus x minus 3 is 2 plus x. And then I've got 5 minus u. So that would be I'll have a negative x, and then I'll have a 5 plus 3, which is 8. So this would be my final answer. You can use this this strategy for a lot of integrals that show up on tables like this. So this is a nice skill to have.